Yeah, just going live. Give me 1 second.
Okay.
Okay, ready?
Okay. Okay, all right. Thank you everyone very much for joining. So we are very fortunate to have Professor Takahiro Sumi as our colloquium speaker today. Takahiro got his PhD from Nagoya University, and he was a postdoc at Princeton and then an assistant professor at Nagoya University. In 2011, he became an associate professor at Osaka University in the Department of Earth and Space Science. And then in 2018, he became a professor at Osaka University. So he's an expert in observations of microlensing exoplanets and has extensive experience with the big microlensing surveys, including MOA. And he's also an expert in discovering unbound or free-floating microlensing planets. And today he's going to tell us about the search for microlensing exoplanets in the near-infrared using the PRIME project, and in the future, the Roman Space Telescope. So for everyone else, please keep yourself muted during the colloquium unless you have a question, and then you can feel free to unmute and ask a question during the colloquium if you have one, or you can save it until the end. So that's up to you. And please take it away, Takahiro.
Thank you for the introduction, and thank you for the opportunity to give a talk here. I'm Takahiro Sumi from Osaka University. I'm going to talk about near-infrared microlensing exoplanet search by PRIME and Lowman. So here's the distribution of the discovered exoplanets so far. Can you see the icon?
Yes, I can see your mouse. Yes.
So the mass of the planets and as a function of the semi-major axis. The black dot indicate the radial velocity discovery, and blue transit, Sheehan, Kepler, magenta direct imaging, and red indicate microlensing discoveries. Here the filled circle indicated the mass is measured, and the open circle indicates the mass is estimated by the Bayesian analysis. And the alphabet indicate the position of the solar system planet. And surprisingly, most of the solar system analog haven't been discovered yet. And also you can see the microlensing is unique to be sensitive to the lowmass planets at relatively outside orbit. So it's very complementary to the other techniques. So here is the current sensitivity of the ground-based microlensing surveys. And we can extend a little bit more by the near future ground-based observation. And then ultimately with the Lowman, we can cover the most of the planets similar to the solar system planet. So here's the same figure, but the semi-major axis is normalized by the snow line. The snow line is here, green line. So you can see the microlensing is sensitive to the planets outside of the snow line, very unique from the other technique. And outside of the snow line, it is known that water vapor became into the ice. So the planet's formation is very active. So by comparing the theoretical prediction by Ida and Lin, they predict many small icy planets outside of the snow line. So the microlensing is sensitive to this region, and then we can compare and test the theoretical model. So here is the schematic of the microlensing. If the lensing object is along the line of sight toward the background star, the light from the star is bent and creates two images. However, if the lens is small, like a star, not a galaxy, the separation is about 100 microarcseconds. So we cannot separate these images, but we can just see the instantaneous magnification, like this kind of light curves. Einstein predicted this phenomena in 1936, but he concluded it's impossible to observe because the event rate is once in millions of stars to be watched. But a half century later, Paczynski suggested then watch the millions of stars to find such object. And then now the microlensing became the real astronomy. So here is a schematic how we can detect the planets by the microlensing. So this is the same schematic. The light from the background source is bent by the lensing star. And if the planet is orbiting around the lens star, and that gravity of the planet can bend one of the images created by the host stars. Then on top of this kind of light clouds by the host star, we can see the small deviation, which called anomaly, in the light clouds. By finding this kind of small, short timescale light clouds, we can detect a planet. So in other words, the microlensing can be explained by the caustics. So you must be familiar with this kind of light pattern on the bottom of the sea or pool. So this is the created by the uniform light from the sun reflected on the water surface and creates many series of the focuses connecting each other. Then this bright pattern is called caustic. So this similar phenomena happening in a gravitational lensing. So if the uniform light shoot from the observer plane to the lensing plane, that light will be bent by the lensing system and then create the focuses on the source plane like this. So this grayscale indicates the density of the ray shooted on the source plane. So that indicating if the source is at that position, then we will see that magnification from the observer plane. So the bright pattern, when the source is on the caustic, the magnification became the infinite. And this magnification pattern depends on the mass ratio of the system and also the separation of the system. So by measuring the light clouds, we can get the mass ratio and the separation. So here is how we detect and miss the planet. So here is the one example of the magnification map created by the primary is at the center and the planet around here. That system creates this kind of caustics and the magnification pattern. If the source is passing like this blue line, we don't see anything other than the primary magnification, like this blue light clouds. And if the planets, if the source passing like this red line, there is a significant magnification due to the caustic around this here, like this blue red line. So fitting with this mass ratio separation and this angle of this trajectory, we can get information of the mass ratio and the projected separation of the system. So the size of this caustics depend on the mass ratio. So the low mass planet signal are rare and brief because the caustic became smaller, but the signal itself is not weak. So we need a large sample with the moderate precision, high cadence observation. And one of the problem on the microlensing is generally we can get only the Q mass ratio, not the mass itself. And we also don't know the distance to the system as well. To measure such physical parameters, we need to observe the high order effect. The one of the effect is the so-called finite source effects. The magnification on the caustic is theoretically infinite, but it will be suppressed because of the finite size of the source. That is so-called finite source effect. And another effect is in the previous slide, I assumed the inertial motion of the planet, the system, and the source stars. But the Earth is orbiting around the sun. So that effect can distort the light curve. This is so-called the microlensing parallax. And also the lens system is, the planet is orbiting around the Earth. That also can distort and changing, also changing the caustic like this. By measuring this effect, we can get the physical mass of the system. So for example, with the finite source effect, we directly compare the size of the Einstein radius and the physical size of the source stars. Then we can get one relation of the mass and the distance to the system like this. And on the other hand, the parallax system, parallax effect, we can directly compare the Einstein radius and also the orbital radius of the Earth, so 1 AU. So from this, we can get another mass distance relation like this. So it's the finite source effect gives this kind of blue line relation in the mass distance relation, and parallax gives another relation like this red line. So that in the cross section indicate the mass, and we can also get such a relation from the lens brightness. So if we measure directly the flux from the lens system, we can get another relation like this purple. Then we can get the mass. So currently we are doing the microlensing survey in the optical. The more collaboration, microlensing observation in astrophysics is conducting such a survey in the Mountain Observatory in the South Island of the New Zealand here. So we are using the 1.8 meter telescope with 80 megapixel CCD. The field of view is very wide, 2.2 scale degree. Thanks to this wide field, we can conducting high cadence 15 to 50 minutes of the cadence observation. Moore is named after the world's largest bird in the New Zealand. Height was, they said, 3.5 meters, 250 kilogram. They cannot fly, but they are extinct 500 years ago, eaten by these Maori people. So here is the observational field of Moore. We are observing just below the galactic center here. This is the galactic center under this galactic disk. We are observing about 20 million stars in a 50 scale degree field. We are avoiding the high extinction region, so it's just below the galactic plane. So we are observing this red circle, we are observing every 15 minutes, and blue circle every 50 minutes, the other field every 1.5 hours. So with this time scale, we can detect Earth mass planet, Neptune mass planet, Jupiter mass planet, something like that. Then we are detecting the 600 microlensing event and issuing alert every year. So here is the typical one exposure towards the bulge. So it's kind of boring images. All of the pixels are filled by the many stars, usually more than one star in each pixel, heavily blended. So to analyze such images, we use a difference imaging analysis. So the high signal to noise good thing reference image will be subtracted from each observed images. Then we can get this kind of subtracted image. All the constant stars are removed, and only variable objects can be spotted, like this blue, black, and white dot. Then we can find the variable objects, and also we can get high precision light curves. So let me introduce how we can detect the planets. First, survey observation by the Moore or Ogu or ChemTNet conducting wide field constant survey observation. Then find the microlensing event real time and issue the alert. So in this case, Moore 2009 bulge 266 event. This event has been found somewhere around here. And then we have been keep watching the progress of the event each night. Then one day, something around here. Here, this bunch of the black dots is the observation by the Moore during one night. We are observing around 10 observations every night. Then observer found the deviation from the expectation from the no planetary model with dashed line. So they indicating the possible planetary anomaly. So they issued a alert. Firstly, the telescope in Israel start observation for the follow-up, right around here. And then telescope in Africa start, and then Chile and Hawaii, and then New Zealand was crowded next night, and then observed by Australia. Then we can measure this kind of one-day deviation from the all around the world. And then this ends up the Neptune mass planet. So this is how we work on the observing the short time scale event. So, but now there are many survey observation, more Google and ChemTNet. So we can, the survey observation constantly measure the target's high cadence. So the survey observation only can even without a lot follow-up network, we can identify the planet lately. So here is another example of we detected 5 Earth mass planets. Here is a magnification by the primary, and in this the tail we can detect a short bump due to the planet. So this event was the smallest planet at the time, and proved the microlensing is sensitive to such a small planet. So here is another interesting example, OGU 2006-109. So this right curve show the 5 distinct features, like 1, 2, 3, 4, 5. And this feature, 4 of these features can be explained by the Saturn mass planet crossing this kind of caustic. But this feature 4 can be explained only by introducing the Saturn mass planet. Sorry, the Jupiter mass planet. So after detailed analysis of this event, we found this system is very similar to our Jupiter-Saturn system. So this is a comparison. Here is the primary was M dwarf, and the planet is 0.7 Jupiter mass, 0.3 Jupiter mass, and the separation is 2 AU and the 2 AU. So this is almost half of our Sun, Jupiter, Saturn system. And the expected temperature at that each planet is also about 70% of the temperature of the Jupiter and Saturn. So it's very close to our system. So this is another one, more 2013, bulge 609. This is the Neptune analog. So first we detect very short one-day timescale magnification like this. So we thought this is the free-floating planet candidate, but after a while, after 40 days, we found there is a long, large magnification due to the primary. So we found that this is a very wide separate small planet. After the detailed analysis, we found that this is very close to our Neptunes. So this is the first case for finding the Neptune analog. So the detection efficiency for this event by microlensing is quite low. So even though the one detection that may indicate such a Neptune analog planet might be very common. The formation of the Neptune in our solar system is not well understood. So it is very important to know the distribution of such a planet. So combining such a detection, we conducted a statistical analysis by using the 3D events found by microlensing. Here is the mass ratio function. The black indicates original histogram in mass ratio, and red is after corrected for the detection efficiencies. So you can see the distribution is explained by the broken power rule, like this. So the break is around 10 to minus 4. So this kind of Neptune or super Earth planet is most common planet outside of the snow line. So here is a comparison to the theoretical model. The blue indicates the model by Ida and Lin with the planetary migration. So apparently there is a large gap between the observation and the model. So the cyan indicate for the case without migration, which increase the number of the heavy planets. But there's still can't explain the gap at 10 to minus 4. So there is some inconsistency between the observation and the model. So may indicate some need some improvement in the model. So here is the frequency as a function of the semi-major axis. So this black line and the shade indicate our result. And that is the 5 times more common than the planet abundance inside of the snow line. So this is somewhat as expected because this, the formation, planetary formation is more active outside of the snow line. And interestingly, that abundance is along this extension of the slope inside of the snow line. So there might be the continuous relation. We don't know. So these results are all the observation by the optical observation. Now we'd like to introduce the PRIME project, infrared observation. The PRIME is prime focus infrared microlensing experiment. We will use 1.8 meter telescope with field of view of 1.5 square degree, mostly in H band. This will be the first dedicated near-infrared microlensing survey. And we will support Lowman by the precursor observation and also the concurrent observation. So we are installing the 1.8 meter telescope at the Sutherland Observatory in South Africa. So the median seeing is about 1.4 arcsecond, and galactic bulge is observable about 50% of the night from this site. So the prime objective of the PRIME project is the 50% of the time will be spent for the microlensing search, and the other 50% will be used for the other science. For the microlensing, we try to study the low-mass planets outside of the snow line, and also try to measure the planet frequency near the galactic center, and we can compare to the results for the other field by the optical. And also we can try optimize the Lowman microlensing field, and also conduct a concurrent observation with Lowman to measure the mass and the distance to the lens system. For the other science, we will do some calibration for the Lowman, and also the TO observation for the transient, gravitational wave, high GGLV, supernovae, or Gaia LARTs, and so on. And we are also conducting the near-infrared radial velocity survey with the spectrograph. Try to get habitable planets around the M dwarfs, and also the near-infrared transit for the M dwarfs. So these are very open, so we welcome any idea. So this is the photo of the galactic center in the optical. As you can see, the very center of galactic plane, many stars are extinct by the dust. So, but in near infrared, we can observe many stars in this region. So more star means more events we can get. So we try to detect, measure the current frequency at the galactic center, which cannot be done by the optical. And by measuring the distribution of the event in this region, we can optimize the Lowman field. And simultaneous observation with Lowman, we can measure the lens mass and distance. And also the time scale distribution around this region, even for the single lens event, we can measure the mass function in this region from the planetary mass to the black hole. From this observation, we can study the structure of the galactic center and also used for the optimizing the Lowman microlensing field. So this is the event rate map towards the galactic center. The red color code indicate the event rate. This is observed by the more collaboration. So you can see the more higher event rate near the galactic center, but you can see some deviations. And the peak is not L equals 0, but the peak is around 1. So to optimize the higher event rate, we need to know the more detailed map, especially where we have no data near the galactic center. So the prime is going to survey around this region. So another advantage is that we are going to measure the mass and the distance to the lensing system by the simultaneous observation with Lowman and the prime. If we observe the one event from the ground and also from the satellite, we measure the light curves with different magnification and different timing of the peak. This is so-called space parallax. So by measuring this difference, we can measure the mass and distance of the lensing system. This has been demonstrated by the Spitzer and the many ground-based telescopes. We are planned to doing the same things by the Lowman and the prime. So here is one example by the Spitzer and the ground base. The red indicates Spitzer measurement, black indicates ground-based observations. In this case, the time difference was 20 days. This is because the separation of the Spitzer and us is 1.2 AU. On the other hand, the separation of the Lowman and us is only about 0.01 AU. So we expect about a 4 hours difference. So 4 hours we can measure the difference well enough, and especially for the around the planetary anomaly, the time, the changing of the magnification is quite steep, so much easier to measure such a small offset. Because the separation is so small, which is more sensitive to the event with small Einstein radius. So that is more sensitive to such something like a free-floating planet. This is the only way to measure the mass of the free-floating planet, like this. So with such a parallax, not only the mass, but we can also get the distance to the lensing system. Here is the distribution of the planets discovered so far. The red indicate microlensing, green is the radial velocity, orange is the transit. So microlensing is uniquely sensitive to the planets very distant from the observer. So by measuring this distance, we can measure the galactic distribution of the exoplanet. So here is the hardware contribution to the prime. For the 1.8 meter telescope, Osaka University and the Astrobiology Center in Japan is producing the telescope. And wide field imaging camera, the Osaka is funding, and the Lowman team is loaning the 4H4G10 detector, and the University of Maryland and NASA Goddard Space Flight Center is manufacturing the camera. Astrobiology Center is currently building the near-infrared spectrograph for the radial velocity survey. And Osaka is providing the dome, and SAO is providing the building. So here is the world, one of the largest class wide field of view near-infrared camera. So University of Maryland is manufacturing the camera at the Goddard Space Flight Center, loaning the 4 Teledyne H4G10 detector from the Lowman team. The field of view is 1.5 square degree. The pixel scale is 0.5 arcsecond. We will cool down the detector down to the 80K. And we have a 2 filter wheel, and we will use the Arcadia electronics, which is the same as what the Lowman is using. So it's a kind of the precursor instrument of the Lowman camera. So this is the more detail of the camera. Here, the overview of the outside. And then within the dual, we have a cold box with cold window. This cold window cut the thermal radiation longer than the 2.5 micron. And then here we have a 2 filter wheel, and then we have a 4 H4G detector here. And then electronics and the cryo cooler is back. So currently the camera is developed at Goddard Space Flight Center. We complete the engineering model last year and did some cooling tests. So currently the flight model is being developed and will be completed by the next June. So in this 2 filter wheel, we have 5 filters. We have a Z, Y, J, H standard wide field plus 1 narrowband filters. In narrowband filters, we have a 1 blank in each wheel, which enable us to use the either a filter in each field. And we also have a dark shutter for the calibration of the detectors. So in the narrowband filter, we have a 3 narrowband in 1 filter like this. Each band correspond within the YJH. So combining with the wide band in 1 field and the narrowband filter in another wheel, we can select which narrowband to use, like this. So this is the optical design of the telescope. The field of view is the 1.56 square degree. The F is 2.29, and 4 collector lenses. The largest one is 45 centimeter. The fused silica, which is high transparency in the near infrared and easy to manufacture and cheap. And all lenses are spherical, which also are cheap. So here is the encircled energy plot. 80% encircled energy diameter is about 40 micron, corresponding 0.7 arcsecond, which is small enough for the median seeing 1.4 arcsecond at South Africa. This is the schematic of the prime focus unit. The 4 lenses, and this lens 2 is movable to adjust the aberration anytime. And then prime focus camera will be attached on top of this prime focus unit. So you can see there is a large gap in the lens 3 and 4, where we can introduce the pick-off mirror for the spectrograph. The light from the primary will be catched by this pick-off mirror, into the fiber to the spectrograph. So this is the Astrobiology Center is developing the South African near-infrared Doppler called the SAND instrument. The science goal of this instrument is searching for the giant planets around the young star, and also searching for the habitable planets around the nearby M dwarfs. The spec is the wavelength is Z and the Y band, and the resolution is 55,000, and efficiency is about 10%. So the point of this instrument is very stable. So the accuracy can be down to 2 meters per second for very nearby M dwarfs. So we constructed a telescope in Japan, and we had a first light at the factory in Japan last September. There is a slit on the roof of the factory, and we observed, I think that was the Denebu, and that here is the surface of the moon. So we confirmed the performance at the same level of 2 arcseconds in Japan. We still need to confirm in on site with better thing, but so far it looks fine. Then the telescope has been disassembled and then departed from Kobe port last February 12, 11. So after we shipped the telescope from the factory to the Kobe, we are stuck at the Kobe port because of we have a difficulty to find the ship. And then we had a 1.5 months delay. This is because the sea transportation confusion due to the COVID-19. They are very short of the container and also the space for the ship. So that is also increased the cost for the shipping, and we have to pay for the storage for a while. So this is the current status of the building at the Sutherland. We have a foundation and a 5-meter pier. But this case as well, we had a 3 months delay because of the shortage of the steel frame all around the South Africa due to the COVID-19. We are still waiting for the steel. But if everything goes well, the building will be completed next April. So here is the schedule. We are here. We're going to install the telescope this year, and we'll start observation. Even though some delays, we are still ongoing, and then hopefully we can start this year. So then we will create a event rate map, and then after the launch of the Lowman, we conduct concurrent observation. Then at least continue the end of the Lowman in 2030. So here is the Lowman Space Telescope. So this was originally double first and recommended by the Decadal Survey, Astra 2010, and NASA's flagship mission following HST and JWST, scheduled to be launched in 2025. The key science is the dark energy, exoplanet microlensing, and tech demo for the exoplanet chronograph. And also they have some guest observing program. So JAXA Lowman J team just joined to the Lowman. We signed with NASA with agreement. So here is the spec of the Lowman. The diameter of the telescope is 2.4 meters, same as HST, given the National Reconnaissance Office. So it was the former spy satellite. The wavelength is 2.6 to the 2.1 micron. Recently, they decided to include a short K band. And the instrument is wide field instrument. The field of view is 0.28 K degree. And also the tech demo chronograph instrument called CGI. The orbit is L2. The mission lifetime is 5 years, and also the serviceable to extend the mission. So here is a photo of the telescope system. So the one key point of this Lowman is this wide field capability in the near infrared. So this is the this white footprint indicator 18 H4RG detectors. The pixel scale is 0.1 arcsecond per pixel. It's 0.28 scale degree in total, which is the almost same as the full moon. So comparing to the previous instrument, it's 80 times bigger than the HST ACS field of view, and 200 times bigger than the IR channel of the WFC3. So thanks to this wide field of view, we can conduct very efficient microlensing survey towards the galactic bulge. So here is the Lowman observation strategy. The 2.5 years will be spent for the dark energy modified gravity survey, the high latitude survey, and the supernova survey. And then 1.2 years will be spent for the microlensing exoplanet search, and 0.3 years will be spent for the coronagraph tech demo. And the 25% will be served for the guest observer. So here is the summary of the Lowman microlensing campaign. So here is the current plan for the observation field of the Lowman near the galactic center, just below the high extinction region. The Lowman is observing about 300 million stars in the 2 scale degree in the galactic bulge, with 15 minutes cadence in 24 hours, 70 days for 1 season. And we are planning to 6 seasons in total, and expecting the 27,000 microlensing events. So here is the simulation by the Matthew Penny for the case of the 2 times of the moon mass of the planets like this. For the typical Earth mass planet, the signal is lasts about 4 to 5 hours. From this Lowman survey, we expect about 1,400 exoplanets. Among them, 200 of them will be less than the 3 Earth mass. And we also expect about some hundreds of the free-floating planets. Here is the sensitivity of the Lowman campaign. The planet mass as a function of the semi-major axis. The illustration indicates the position of the solar system planet. The Kepler measured the planet distribution inside of the Earth orbit. On the other hand, the Lowman campaign is sensitive to the outside of this region. And the Lowman is sensitive to all the solar system planet except Mercury. And combining with Kepler, the Lowman can complete the statistical census of the planetary system. Then we can test the planetary formation model. So another interesting feature of the Lowman is because of the very sharp imaging quality, we can detect the light from the lens directly. The typical lens source relative proper motion is about 5 mass per year. So that gives 0.1 pixel over the 4 years. So we cannot resolve, separate this light from the source and lens. We can see the elongation of the PFS because of this proper motion. If we subtract original PFS from the elongated PFS, we can see this kind of pattern as a residual. From this, we can measure the lens mass for about 70% of the planetary system, which is complementary to the mass measurement from the parallax observation. So as I said, JAXA signed to the NASA to join into the Lowman. Here is the Japanese contribution package for the Lowman. So one is the Subaru-Lowman synergistic survey using the 100 nights from 2025. We already have a commitment for that. And the second is contribution to the coronagraph instrument. We are providing the polarimetry optics and the coronagraph mask substrate. The third is the K-band data downlink station in Japan. And the fourth is the ground-based microlensing data sharing. We produce the more light curves for the pipeline development. And also the precursor and the concurrent ground microlensing observation by the prime telescope. This is also one of the contribution from Japan. So as for the synergy with the Lowman and the Subaru, we both have a very wide field view and high sensitivity, but we have a different wavelength capability so we have a very good synergy with that. So as I said, from the ground and the space, we can measure the space parallax. So by using the Subaru HSC and the Lowman, we can also measure the parallax, as I said, in the prime. But we can do much deeper. Another option, so the first option is a hyper supreme cam, which is a very wide field of view optical images on Subaru. But another option is the ultimate Subaru. This is the near future instrument, wide field infrared imager with ground layer adaptive optics. So due to that, we can achieve about 0.2 to 0.3 arcsecond full width half maximum for the 14 arc minutes at the K-band. In the K-band, we have a less extinction in the galactic bulge. So we can do the better observation for the near the galactic center. So with this observation with ultimate Subaru or HSC, we can measure the mass of the free-floating planets and other bound planets. We can also fill the gap of the Lowman campaign, measuring the orbital parallax for the black hole and also the lens parameter for the other bound planets. With high resolution, with less blending, we can detect more faint objects. Then we can measure the mass of the lens system and also the hopefully astrometric microlensing for the black hole event. With K-band, we can measure the metallicity of the M-dwarf Foster combining with other Lowman band. So here's the summary. The prime is the first dedicated near infrared microlensing exoplanet survey. So we try to measure the planet frequency near the galactic center to be compared to the previous measurement by Optical. We also try to measure the galactic distribution of the exoplanets and optimizing the Lowman observation, and also conduct simultaneous observation with Lowman to measure the lens mass and distance. We are going to the follow-up transients, gravitational wave, GRB, etc. And Lowman will complete the statistical census of the exoplanets. And the synergistic observation with the Subaru also enhance the Lowman. Thank you.
Okay, thank you so much, Takahiro, for a very nice talk. If anyone has questions, you can click the raise hand button on Zoom. And I see there's a question now. Go ahead, Kaylin.
Hi, Taka, Kaylin here. Thanks for that talk. I'm wondering, do you have an estimate of the fraction of events or planetary events in specific that Roman will detect that will be detectable with prime and that will have robust parallax measurements?
Not precise measurement estimate, but we sensitive to the events with down to the about 18.5 magnitude in H band. So only the bright object we can detect.
Okay, thanks.
Okay, I think the next question from Sebastiano.
Yes, hello, great talk, Taka. I want to ask about the data policy for the prime microlensing campaign, if the data are going to be public or not. Thanks.
So this is the also the part of the NASA project. So it's we will follow the NASA data policy. So we are trying to release the data public as soon as possible. But it's depend on the our ability to the archiving, depending on the funding. Yeah.
Great. Thanks.
Okay, I think that Shri is next.
Sumi-san, konnichiwa. I had a question, which is the infrared spectrometer.
Mm-hmm.
You have a unique ground-based imager in the near infrared, and for a while it's sort of like the one, very good pixel size, reasonable aperture, large field of view. That's pretty unique.
Mm-hmm.
The spectrometer, I'm afraid, is not unique, nor is it very powerful.
Mm-hmm.
There are much better spectrometers already available, for example, on CFH, which goes across the entire near-infrared band, or at the habitable zone, infrared, the spectrometer on HET. So why are you wasting your observing time on a simple YZ spectrometer?
Okay, good question. First of all, the people in the astrobiology center is interested in this survey, and then they are funding to use that part of the telescope time. So so it's a separate project, and we are mostly interested in the galactic bulge observation. The bulge is for the the microlensing survey. The bulge is only observable 50% of the night. So the other time, each partner can do their own science, whatever they want. And on their, so that's what they want. And on their side, they have a similar instrument in the Subaru. And they conduct a large survey for the M-dwarf. But with Subaru, they can do much deeper and fainter object. But the telescope time is very limited because of the high competition. So what they want to do is that they want to use this instrument for the very nearby long-term survey with very nearby bright object. Because relatively the telescope time is relatively easier to get, so it's more suitable for the long-term observation.
Okay, so I understand. It's not a science decision then.
Yeah.
Okay. Next question is from Sean.
Hi, Taka, great talk. I was just wondering if you could comment on how the PRIME survey compares to the UCURT microlensing survey, and if you could just maybe talk a little bit more about how PRIME will influence Roman field selection.
Okay, so for the Euclid, we can do the similar observation as the Lowman. So during the time, if the Euclid decide to do the microlensing survey, we can do the concurrent observation to measure.
Oh no, Taka, I'm sorry, not Euclid, UCURT.
Okay, sorry.
Yeah, the UCURT microlensing survey that was done on the ground already. Yeah.
There was the survey, precursor survey by the UCURT before, and they have found some events and the planets. It was interesting. That was also one of the motivation we started. But that telescope time is very limited. So the advantage of the PRIME compared to the UCURT, of course, UCURT have a much better image quality with better sight. the advantage for us is we can use a dedicated telescope so that we can conduct long-term and more high cadence observation. That is the advantage.
Okay, thanks.
Mansi, do you have a question?
Yeah, I do. So first of all, I just wanted to wish you all the best for commissioning Prime. Exciting times ahead. The question I had for you was, what were your plans for a real-time data reduction pipeline to look for transients and variables beyond just the microlensing events in the Prime data stream?
So you asking transit?
Yeah, transients, variables, anything that changes, like for a time domain pipeline.
Yeah. So especially our member in the University of Maryland are interested in the transient. They have a different other telescope and instrument for the transient. So we will join to that observation. And also the David Buckley in South Africa, they are also joining to the network for the transient, so that they have their time for the prime as well. So they will use the fraction of the time for the transient for that kind of network. So that network is their prime for as a contribution to join into the Lowman as well. So we, in the agreement between the collaborators, we have the plan for the TOO by sharing the telescope time between each collaborator. So each collaborator can initiate TOO anytime. And then we can compensate the telescope time later.
Yeah, I was actually not asking about the TOs, but even during the prime survey, you'll be repeat observing different fields, right? So during that time, is there any plans to reduce the data in real time and issue alerts for anything that changed completely serendipitously, no matter what else the telescope is observing at that time?
So as an alert towards the bulge, we reduce the real time and issue the events about within the hour of the observation. And for the off bulge, we can use similar same software for the other bulge, not non-bulge field, but we haven't planned yet. So it's still to be considered. So we have enough server to conduct the real-time analysis on site. So because of the network is very thin towards the South Africa, so everything should be on site.
Okay. I have one question as well. I might have missed it, but I'm interested in the simultaneous observations with Roman. So is the plan to take concurrent observations with Prime during all of the Roman microlensing observations for the whole 1.2 years?
Yeah.
The whole time, okay. That's
yeah.
Great, okay.
Because we are going to observe the bulge anyway, whenever possible.
Mm-hmm. Okay, do we have any final questions? We're just at the hour. If not, then please join me in thanking our speaker, Takahiro Sumi, for a very wonderful talk. Thank you.
Thank you very much.
And I will pass the mic over to Mansi or one of the faculty hosts.